Okay, so 8.1, the equation of a line in 2D and 3D space, 2 and 3 space. Okay, so let's recall grade 9, we did study the equation of a line with the slope and y-intercept, and we've used it since many times. Y equals mx plus b. We also have point slope form of a line, standard general form of a line. And here we are with vectors. We now have a way to express the equation of a line using vectors, okay? And now this can apply to both 2 space and 3 space. And so the vector equation of a line is given as follows. We have xy, a point xy, a point vector rather. It's about the representation of a point on this line is a point vector, and that's equal to an existing point vector on the line plus some scalar parameter t multiplied by a direction vector. So think of direction vectors kind of like your slope, right? You're using the letter m. So it gives us the direction of the line. So here's how this is represented visually. We have a line. Let's call it the line. There's a point A on this line. There's a point P on this line. But this is the line we're talking about. We're trying to create the equation of this line that I'm highlighting right now. So any point on this line, let's say we're trying to find the point P, right? And that point P, we can create a point vector, right? So we create a point vector starting from the origin to that point P. We know that point P has the coordinate xy, but as a point vector from the origin, we say the square brackets xy. So instead of saying coordinate points, we're just going to express these things as point vectors. Now to create the equation of a line, a vector equation of a line, in terms of in terms of vectors, we need to know what is we need to know an existing point on that line. So let's say we are given point A, and we're going to express the point A as a point vector. So again, from the origin, point A is a point vector, and as long as we have that point vector plus the direction vector, so here you have the direction vector m. In what direction is that going? Well, as long as we have where that direction vector is going, then we know the direction that the line is acting on. So as long as we have m and some scalar multiple of m, right? So that's why we have the parameter t there. So tm, then we can reach any point from that line. Just starting from the point vector a plus some scalar multiple of direction vector m, we can reach any point p on that line, and p is any point that we want on that line. Okay, so that is what this equation here represents. That point vector xy equals some starting point vector a1, a2 plus some parameter t times the direction vector m1, m2. Okay, so as long as we have that, we have the equation, the vector equation of a line. And we can use that idea to create vector equations. So here's one example. Let the point A, 1 and 3, be a point on the line with a direction vector m. Write the vector equation of the line and find 2 other points on that line. So that this coordinate point A can be written as a point vector, right? Joining from the origin O to that point A. So as a point vector, this is simply square bracket 1 and 3. So my vector equation of a line, represented by the vector xy, the point vector xy, is equal to some starting point, which is what we are given, 1, 3, plus some scalar multiple of the direction vector, so t times -2 and 5. Okay. Now to find any other point on this line, we just need to just arbitrarily choose different values of t, right? If I said t was equal to 2, then I can come up with another point vector, another point on this line by saying, okay, 1, 3 plus 2 times -2 and 5. We can then simplify the right side. 2 times negative 2 times 5. Well, that's going to be a vector of negative 4 and 10. When added to 1 and 3, I just add their components, and so I get an xy point on this line as 1 plus negative 4 and 3 plus 10, which is negative 3 and 13. So there's a point on this line, but just arbitrarily setting that scalar parameter t equals to 2. I can make t a negative as well, so if I could choose t equals negative 2, and we could say, well, the point xy is equal to the starting point 1, 3, plus negative 2 times negative 2 comma 5, the direction vector, and then when I multiply them out, negative 2 times negative 2 is positive 4. 4 plus this one over here is equal to 5 for my x component. And then negative 2 times 5 is negative 10, plus 3 there is going to give me a negative 7 for my y component. So here's another point vector on the line. So here I have two possible two answers. Here's a point vector, negative 3 and 13, and here's 5 and negative 7 as points on my line, just because I made those parameters t values the way they were, 2 and negative 2. And if you put in any other t parameter, you'll get a different point on that line. Okay. All right, so that's vector equations. Now, we also have something called parametric equations, which means we just take the vector equation and rewrite them for their specific components, right? So if I take this vector equation, I can multiply the scalar parameter t with my direction vector to inside their components of that direction vector, and then I can use my rule for adding two vectors by just adding their individual components, the x component and the y component. And now the parametric equations are simply just separating the components and writing them as separate equations. So I have x component equals the x component of that right-hand side. And sorry, this is a little bit mistake. Tm, I should say tm subscript 1. And then the y component of the right side. Okay, and these are called parametric equations, and they can be useful when we start solving for certain things. So example 2, a line passes through the points P and Q. Find the vector and parametric equations of the line. So I need to create a vector joining these coordinate points. Remember, these are coordinate points because they are round brackets. So then create a vector by joining P and Q, and we're going to call that our direction vector M, because if I create a segment from P to Q, that's P and Q, create a line segment, but if I extend that line segment, okay, yeah, we really have a line, right? And P and Q just essentially becomes my direction vector, right? That's my direction vector. So M is my direction vector. If I now, okay, how do I find the direction vector using two coordinates? So again, it's going to be the second coordinate minus the first coordinate component. So 2 minus negative 3 and 5 minus 7, which is 5 and negative 2. So there's my direction vector. Okay, and to create my equation of a line, xy, okay, there's my point vector equals a starting point vector. I need a point vector that's already on that line, and so I can use either P or Q. So I just turn them into point vectors. So if I turn point P into a point vector, I have negative 3 and 7, so there's my starting point, plus some parameter t multiplied by the direction vector 5 and negative 2. And so there's my vector equation of the line. And if I wanted the parametric equation, so what I'd be doing is if I add both of these vectors together on the right-hand side, I would have negative 3 plus 5t and 7 minus 2t. And really what I want to do to create the parametric equations is just take the x component, okay, and then write it as x equals negative 3 plus 5t. So you're taking the x component on the left, equating it to the x component on the right. And same thing for the y component. The y components are equated here too. So the y equals 7 minus 2t. And those are my parametric equations of the line. Okay, and that brings us to a third type of equation, which is our symmetric or scalar equation of a line. Okay, And so we're going to let any point P be a point on the line which passes through point A. So here's point P, and let's say there's point A down here. We're going to let this n vector be the vector capital A, capital B, and this vector is a normal vector to this line, right? So this is a normal vector so it's 90 degrees to the line. So if we use that normal vector, that idea that it's 90 degrees, then I could say, I can use the property of the dot product saying that two vectors are 90 degrees to each other, their dot product is going to be 0. So two vectors, I'm going to take the dot product here, our vector n, the normal vector, and the vector that I create by joining point A to point P. And if I create that dot product and then subsequently multiply it out algebraically, here's what I get, right? I get the normal vector, which is capital A, capital B, dotted with the vector created from point A to point P. So remember, point P is just any point on the line, right? X, Y, right? And point A is a known point on the line, so A1, A2. And so A1 and A2 are the constants here. So if I'm creating the vector from A to P, I'm just taking the point P, subtracting with point A, point P, subtracting with point A, and those are their components. And then I multiply them out, right? I multiply them out algebraically. A times X minus A1 plus B times Y minus A2. And then if I expand that, I get A times X here, A times A1 over here, B times Y here, and then B times A2 over here. Now, AX and BY are what I'm going to keep, okay? Because X and Y are the variables. Obviously, point P is the moving point. A and A1 and B and A2 are constants, right? Those are constants. We always know what A1 and A2 are. Those are the starting points. So if we resolve those as just a single constant C, then I can now express the scalar equation of my line, ax plus by plus c, which looks very much like the standard form of a line, except here, when you read a scalar equation of a line, a and b are automatically the components of the normal vector. Okay. Now, the most important thing about this is that this only applies to lines in 2 dimensions, right, on the xy plane, not in 3D. Okay. Vector and parametric equations of a line do apply in 2D and 3D. Okay, but scalar equations only apply in 2D. So as an example, find the scalar equation of a line with normal negative 3 and 5 and passes through the point A, which is 2 and 7. Okay, so my normal vector n is negative 3 and 5, and then we have a point A, which is 2 and 7. Okay, and then the point P is any other point on that line is represented by x, y. Okay, so if I create a vector joining A to whatever point P that I want, the vector would look like this, right? So I just subtract x minus 2, and then y minus 7. Okay, so there's my vector there, and then my dot product n dotted with AP, because the normal vector has to be normal to that vector AP, would then be the dot product between negative 3 and 5, dotted with x minus 2 and y minus 7. And if I do this algebraically, I'm going to have negative 3 times x minus 2 plus 5 times y minus 7. And expanding and simplifying results in negative 3x plus 6 plus 5y minus 35, and that's equal to negative 3x plus 5y minus 29, and we know that dot product is supposed to equal 0. And so there, right here on this line, yes, I know it's equal to 0 because the dot product between a normal vector and the vector should be 90 degrees. So now here, this on the right side, we see something that looks like that scalar equation form ax plus by plus c, with negative 3 and 5 being the capital A, capital B. That is your normal vector, and that is the scalar equation of the line. Okay. So here's a note: the line passing through the point P with a position vector R0 in 3 dimensions and direction vector in 3 dimensions has a vector equation as well, So we can express vector equations in 3 dimensions, similar to what I showed you in the previous examples. In the first example, just adding an f and z component at the end. Same thing for the parametric. You just add the z component at the end. Okay. Sometimes you may need to solve for t. Okay, and so it might be useful to rearrange these parametric equations into the form x minus x0 over m1, which would equal to y minus y0 over m2, which is equal to z minus z0 over m3. And so all I'm doing is just kind of moving these over, right? So you get x minus x0 and divide that by m1, right? And you do that for all 3 components, and they're equal to each other because they all have to have that common parameter t. That t parameter has to be the same in all 3 equations. Okay. All right. So again, another important note that the scalar equation again being ax plus by plus c equal to 0 cannot be used to define a line in 3D space. Okay. Later on in the next lesson, we'll talk about how that scalar equation defines a plane in 3D space. But here, the only thing we can do in 3D space are vector equations and parametric equations. So here in this next example, we're going to write the parametric equations of the line through the 2 points in 3D space. So I'm going to create the vector of between a and b in 3D space. Okay, and that vector is, well, okay, 4 minus negative 8 is 12. 1 minus 1 is 0, and 2 minus negative 2 is positive 4. So there's my vector in 3D space that joins the 2 points A and B. So if I had A and point B in 3D space, okay, I created a direction vector, but really I'm trying to find the equation of the whole line. And so my vector equation, any point vector expressed on that line, x, y, z, is equal to, I need a point that I already know on that line. So I could pick, let's say, point A, and you could pick any one between the two. I could pick point A or B, and if I pick point A, I'll just write down that point vector, negative 8, 1, and negative 2, plus some scalar parameter t times the direction vector, 12, 0, and 4. So that says I can get any point on this line. I can get a point up here, right? If I start from point A and I multiply by some scalar multiple of the direction vector. Okay, and then I arrive at any point P. So that's the vector equation. If I want the parametric equation, again, what I'm doing is I'm taking the x, making it equal to the x components, right, including the parameter t. So x equals negative 8 plus 12t. Same thing for the y components. Y equals 1. Take the y components of each plus 0t, but I don't need 0t. I can just write that as 1. And then z equals negative 2 plus 4t. Do I need a parameter t in each parametric equation? No, I do not. This just says no matter what point I come up with, the y value is always going to be equal to 1. Okay. All right. So, question follow-ups to this question is the point C1, 2, 5 on the line? Well, okay. First of all, if y is always supposed to be equal to 1, and then seeing a 2 here, well, no, this is not going to work. So no, because the y component for this point here is not equal to 1. It needs to be 1. What about for part B? Well, we do see a y component of 1, but is it on the line? Well, let's check. You take your parametric equations. So again, we're going to take these parametric equations here. We're going to put x, y, and z, substitute those in with the numbers are given here. So for fx equals 1, so we're going to make the left side equal to 1. The right side is negative 8 plus 12t. If y is equal to 1, the right side is equal to 1, so we're good there. And then the z component 5 is equal to negative 2 plus 4t. Now the question is, if I solve for t, are they going to be the same, right? Because that parameter t has to be the same, right? Because in the vector equation, there's only one t in the vector equation here, and that applies for all 3 components. So that t has to apply to both that x and z component. So if I solve for t for the first one, I get 1 plus 8 over 12, which is equal to 9 over 12, which is equal to 3 over 4. Okay. If I solve for t in the second one, I get 5 plus 2 over 4, which is 7 over 4, which is not the same. So since the t's aren't equal, what do you say? Well, we say that point D is not on the line. Okay. What about point E? Same idea. So let's put part C here. Part C is 1 equals negative 8 plus 12t. 1 equals 1. We're good there. 1 equals negative 2 plus 4t. Solving for t, I get 1 plus 8 over 12, which is 9 over 12. And there's my 3 over 4. And for this z component, 1 plus 2 over 4, which is 3 over 4. And yes, both have the same values of t, so therefore E is on the line. All right, so you have to just look at do they have the same parameter t? And if they do, they're on the line. For my final example, determine the vector equation of the line that is parallel to the z-axis that goes through the point P. Okay, so parallel to the z-axis. Okay, well, the z-axis, what vector do we know that describes the z-axis? That is going to be our unit vector k. Okay, so remember, unit vector k is equal to 0, 0, 1. Okay, and if that vector equation line is going to be parallel to that unit vector, then I'm going to say my direction vector is 0, 0, 1. Okay. So my equation of a line, my vector equation of this line, x, y, z, it's going to be parallel and has to pass through that point P. So I'm going to turn that point P into a point vector. So negative 4, 3, and 7, plus some scalar multiple t times the direction vector 0, 0, 1. And that's going to be my vector equation. Okay. If there was a follow-up to say what's the parametric equations, you would just simply write x, y, z equals, 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 create 3 equations, write down the components of your point vector, plus, plus, plus. You can put 0t, but you don't have to. You don't have to. And the last one's going to be just a single t, 7 plus t. So those are going to be my equation in parametric form. And again, you don't need to write 0t, so I can just erase those two. Okay, so that is the video lesson for 8.1.